Welcome back to the Predictive Analytics Regression and Classification course. This is lecture 3, part A. In this lecture, we will focus on understanding the normal equations and how different issues of normal equations. So, we will start with a simple regression model which has, say, n rows and p columns. Now, what I mean by n rows, p columns, n is the number of samples. So n is the number of samples and p is the number of predictors. Okay. So xij is the ith row and jth column. So this is ith row and jth column. So basically xij stands for jth predictor of the ith sample. Xij is the jth predictor of ith sample. Now, y is n rows, so n responses that we have here, n responses. This is the design matrix or X matrix, and these are the residual errors vector. Now, many different models you can fit, but before that, so it is convenient to include a constant variable once in X. So suppose you have these are the predictors, and then what you can do, you can make the first predictor as all ones. If you do that, then automatically this will be your constant predictor. Okay, it will be your intercept. It will behave as an intercept. Okay, if you just make each of basically xi1 equal to 1, then it will behave as a first column will behave as an intercept. You take each of them as 1. So in this, all you have, the data that you have is y and x. So y responses and x predictors. And we want to estimate the coefficient values. So this is our main goal, that how to estimate the betas. That is what we want to estimate. So there are many different methods to estimate the beta or the regression coefficients. The most popular is Leats Square method. Now, minimizing how the way Least Square method works is by minimizing the least square or the residual sum of square. So why it is called residual sum of square? So you see your model is y equal to x beta plus epsilon. So you can write this model as epsilon equal to y minus x beta. So essentially this epsilon is y minus x beta. So if you take epsilon transpose epsilon, that will be basically the residual y minus residual sum of squares, x minus x transpose y minus x beta. That is what you are getting. Okay. Now this is same as, you can write it as I equal to 1 to n yi minus xi transpose beta is epsilon I square. So I don't need this thing. Yeah, epsilon I square. So our objective is to minimize the sum of squares of error. That is our objective. Now what happens with how the sum of squares of errors behave. So if you look into the sum of squares of errors, so this sum of squares of errors, my yi's and xi's are essentially known to me. It is from the data, nothing to change. It is exactly constant. Effectively, it is behave like a constant. Now, only thing is unknown to is beta. If I change a beta little bit, so naturally this epsilon I square will change. Now, if I sum of epsilon I square also change, so RSS of beta is a function of beta. RSS, residual sum of square, turns out to be function of beta, because if I change beta a little bit, so residual sum of squares of beta will change completely. So if you look into the surface, if you can consider this is like intercept, different values of intercept, okay, and different values of slope. For different values of slopes and intercept, you plug it in there and then you calculate the residual sum of squares, and what you get is surface. Now obviously I would prefer that slope, and somewhere here maybe let me try a different color, maybe blue. So I will probably try to reach here by maybe this value here and somewhere this value. So these are the values where we will get a most minimum value. So where the value is minimum, we will try to get there. Okay. Now its minimum always exists. Turns out we can show that it minimum will always exist, but may not be the unique, and we will discuss what I really mean by this. Minimizing residual sum of square of error. So essentially, how can we do that? We can do that by just differentiating residual sum of squares of beta with respect to beta. So, and set it equal to 0. So we will differentiate and set it equal to 0. If you then, what we will have is essentially we will set up an equation, and that equation will give us the solution for, if we solve that equation, we will solve, and that will give us the solution for beta. Now, if we differentiate with respect to beta and set it equal to 0, what we get is typically known as the normal equation. Now, if you look into this normal equation, what we have is x transpose x. Now, x is a n cross p, so x transpose is a p cross n matrix, so x transpose x is a p cross p matrix. Similarly, so this is x transpose x is a p cross p matrix, and beta is a vector of length p. So here on the left side we are getting p equations, and on the right side we have x transpose y. So x transpose is p cross n and y is n cross 1, correct? So x transpose y, p cross n, n cross 1, it's giving us p cross 1. So we setting up p linear equations with p unknowns. These are the p unknowns with p linear equations. So the normal equations turns out to be this. This is my normal equation. Now what I am doing, I am bringing the typical popular notation of linear algebra. Let us call x transpose x as A and x transpose y as B. then we can re-express our normal equation as Ax equal to B, where A is a P cross P known matrix, B is a P cross 1 known vector, and X is actually my beta. So X P cross 1 is unknown coefficient. And this X we want to solve. Now suppose that for known matrix A P cross P and the vector of B P cross 1, a P vector of length P, we wish to find a vector P such that this is the system of equation. So that the standard approach is ordinary least square linear regression is just minimize this square under the Euclidean norm, and the solution will be A inverse B. Then the question is, what happened? A is not invertible. What happened then? This is a big question. If A is invertible, then we are very good shape. We have a solution for the system. But if it is not invertible, then what we should do? Now we have to figure out when the solution, what happens if, under what condition solution does not exist, under what condition solution does exist, and all these situations. The first thing that happens is if the rank of A augmented B is strictly greater than rank of A, then solution does not exist at all for the system of equation. For that particular system, solution will not exist. So this is completely out of the window. Second situation is, second condition is if rank of A augmented B is equal to rank of A, then you can ensure at least one solution exists. There could be more than one solution, but at least one solution do exist. Third situation is if rank of A augmented B is equal to rank of A, and that is equal to P, that is A is a full rank matrix. That is very important. If it is a full rank matrix, then A inverse uniquely exists. So that means the solution A inverse B is unique. So that is very important. So that means if A is a full rank matrix, then the solution, we have a unique solution. Now and the fourth situation is if rank of A augmented B equal to rank of A, but it is less than P. So that means A is less than full rank matrix. Then X has infinitely many solutions. And this is considered as a ill-posed problem. If you have this kind of situation, this is considered as ill-posed problems. Means the solution, you may have a solution, but you have infinitely many solutions. And that is very difficult. That means effectively you are saying that every possible value on the real line could be a solution. If you have infinitely many solutions, and that is not really helpful. So this kind of situation are being called ill-posed problem, and we will often face these ill-posed problems. Now we have a theorem for normal equation. One can show that rank of X transpose X is equal to rank of augmented X transpose Y equal to rank of X transpose X. This is, you can show. So what does it mean? So if you have a normal equation like X transpose x beta equal to x transpose y. So all you have to do, if you have a data, all you have to do, you have to set up the normal equation, and this theorem guarantees that you have at least one solution. So if you go back here, it says that the second is true for whatever be the data. Whatever be the data, second is true. That means at least one solution exists. So this is very strong. So whatever may be your data, irrespective of that, you have at least one solution. The normal equation guarantees at least one solution, whatever may be your data. Irrespective of that, normal equations guarantees, that is a very strong result, we have at least one solution. So I am not going into the proof of the theorem. I am leaving it for you to figure it out. It is very simple to prove this theorem. But what I am going to do, I am going to explain you the implication of this theorem. So at least one solution always exists if you adopt at least square method. If you adopt any other method, we don't know whether the solution exists or not for that method. But if you adopt a least square solution or least square method, then at least one solution is guaranteed. Now, if x transpose x is non-singular, that is rank of x transpose x is p, then unique solution is given by just simply x transpose x inverse x transpose y. So this is the solution that we have for normal equation. So all you have to do, that once you have the data, you have to set up the normal equation, and then this is the analytical solution for the normal equations. Next, you can ask yourself, can we use mean absolute deviation? So we are using least square method. In the least square method, what we are doing is we are trying to minimizing RSS of beta, which is essentially trying to minimize I minus xi transpose beta whole square. I runs from 1 to n. It is trying to minimize this residual sum of square. Now here question is, can you try to minimize this absolute deviation? I would recommend that you pause the video, think about this problem for about 5 minutes, and then come back and let us discuss. I hope you got the solution. Let us discuss what can we do. So conceptually there is no problem. Certainly you can use this mean absolute deviation. You can do that. We can try to develop some numerical solution. Some numerical solution certainly can be developed, but we do not have any guarantees, any theoretical guarantees that for sure we will have at least one solution. Also, one of the reasons that it is difficult to have an analytical solution, because if you use residual sum of square, it behaves like sort of a nice continuous curve, elliptical curve. So it is differentiable at 0. It is continuous and it is differentiable at 0. But the problem with this mean absolute deviation is it is continuous, but it is not differential at 0. It is not differentiable at 0. So you cannot really set up take a derivative and set it at 0, and because at 0 it is not differentiable, and try to find the solution. So that is the main problem with mean absolute deviation. Now we will consider a problem, an exercise. Suppose there are 4 boys and 4 girls, and their heights recorded as follows. So there are 4 boys and 4 girls, and these are their heights. So we want to model height as a function of gender, boys or girls. So we said that okay, beta naught plus beta 1 times boys. And then we are saying that if it is boys indeed, then we will do a one-hot encoding, or we'll create a dummy variable for boys like 1 1 1 1. First 4 values are ones, and then next 4 values are zeros, and first set of values are all 1. Let's create an intercept. Then so our model is height equal to beta naught plus beta 1 times boys. So we want to estimate the beta naught and beta 1. So what we do, we compute first x transpose x, which gives me 8, 4, 4 and 4. And then x transpose x inverse is this. And then beta hat is x transpose x inverse x transpose y. We solve this, and this is our beta naught hat, and this is our beta 1 hat. Now what we have here, so this is our model. Now our fitted trained model is height equal to 163 plus 1.25 times boys. If a new test point is a boy, then expected height is 163 plus 1.25 times 1, because for boys we will take 1. So that gives us expected height to be 164.25. And if a new test case is a girl, then expected height is 163 plus 1.25 times 0, which is 163. So that's how we can handle the dummy variable also, or the categorical variable also. So in the data set, the gender is a categorical variable, or gender is a categorical or string variable. Categorical or string variable. Okay, so whenever you got a categorical variable or string variable, you create a one-hot encoding or create a dummy variable for a label, and then like 1 1 for boys in this case we created. You can do it for the girls also. It will be nice exercise to do it for the girls and check how, if the intercepts, what the intercept values and what is the beta 1 values you are getting, and if you are finally getting the same answers or not. Check it out, and we'll get back in the next video.